Okay, if you remember, power law is just taking the power of that, right? Okay, so let's say if you have gamma equals to some high value like greater than 1, 1.2 or maybe 5. Okay, so what will happen is that here, what are the values? Let's say from 0 to 255. So let's say that here I take 100. So what will be the value if gamma is maybe, let's say 2? Gamma is 2, yes. 10,000, right? But here if I have a 10,000, okay, so what? No, but what we have to do? At 10,000, do we expecting 10,000 in our image? What we do?
Some normalization.
No, we have to do normalization, right? So when you do the normalization, your curves become different. This is because of the normalization.
Normalization. What's the denominator?
Yeah, I give you the expression for that. First, you have to minimize to 0 and 1. Okay, you remember that? So minus what? Minimum value. Okay, then divide by the maximum minus minimum to get the 255. Okay, the formula that
This is a vector composition, right?
yes, exactly. Otherwise, you can do it. There's general formula there. Okay. So one way is this one. Okay, to understand it. The other way, because you see here, it does not make sense. This is 0 to L minus 1, 0 to L minus 1. But since I am transforming the image, the transformed image should have the same intensity level. Okay, so once you convert it, you normalize it. This one way. The other way is, or you normalize it between 0 and 1. The original image between 0 and 1. How to do that? Divide by 255. Okay, so it becomes 0 to 1, and then you just do it. All this calculation, so it will also this will become 0 to 1. The maximum will be still 1. So if you normalize first, you will already get the S value transform as 0 and 1, and then multiply with 255 to get back. In that case, if you have 0 to 1, the R will be fraction, and if R is a fraction, these terms will make sense. So there are two ways: either do normalization, because we already said that we have to normalize it. So if you do that, therefore I think we do not specify here. So you have this problem. Okay, how we do histogram equalization? Yes, for histogram equalization, how we do equalization? CDF. So the level minus 1 into CDF will give you the transformation that we use. But however, it is not always good. Okay, we have seen that if it is very dark, maybe because of the very dark, the CDF will be very high. Okay, at the end, at the start, and become flat. Because of this, if I transform the image, the lower parts which are dark now will become very bright. So this becomes this. Okay, so what's the solution? What's the solution? Yeah, the solution is that instead of directly doing this, I can do equalization to get some idea that what it will look like. Okay, the CDF, and then I can specify something near to it. Okay, to make not that much bright, but in the middle. So let's say I can do something like this. Okay, which is very close to it, and I'm making sure that the lowest one, which was dark, should not become very bright, but it should be like in the middle. Okay, how to do this now? We do histogram matching or specification where we specify the histogram. Okay, in order to specify another histogram that you want. Okay, so how to do this? First thing is you make the image transform using the same histogram equalization technique that we have said. Okay, so now it becomes a flat, ideally uniform or flat PDF. Yes or no? Okay.
So, Victor, if we go back to that picture, we still will have that bright picture. The one we for the one. So
yes, here still we have the black, but mathematically I want to show you that what we are doing. Okay, the problem is that directly we cannot go from one end to the other which I specify. So you cannot do that. Okay, so what I will do? Okay,
You will do
yes. So what I will do? Let's say I have two histograms that I want to transform. One is the original image, the other I want it, right? Okay, so I cannot. There's no direct way to do. So what I will do? I will do the histogram equalization of both of them. So if I have the histogram equalization of both of them, they both will become ideally uniform. So I can equate it, and after equating, I can go back to the one I want. Okay, but actually the example I told you here, when I did this, I get this. So if I think that why I'm getting so bright, I want not this sharp thing. So this is what I did. I just tried to specify my own CDF. Okay, that CDF, then I tried to map the
trial and error.
And not a trial and error based on my experience. Okay, okay. So you get the point. Now both the one I want, the one I have, both I make it flat. Okay, uniform PDF. So it means that if I do this one, it should be equal to this, right? SK. Yes. So it means that what it means is this, that G of ZQ is equal to SK, right? Yes. What is G of ZQ? Is basically transformation on Z, which was like here, it was transformation of R. So what is R? Is my original image. What is Z? Is the what I want. Okay. So this is the transformation. Now in order to find out
desired,
I will do this inverse of that. Okay. To get the image I want.
Second one,
Yes.
like you want that image. So that's some reference value or any random variable.
Again, yeah, I give you an example. You see this here? I give you this example here that based on once I do the equalization, I found out that this is very bright. So in order not to get very bright, I just make a curve slightly down, okay, just to make a bit flat. So that should not be very bright. So based on my experience, I said no, this should not be the case. This should be somewhere here. So this is my PDF. Now I get the PDF. Okay, just a second. So what I did, I just transform it to the uniform PDF, both of them, and then after getting the uniform PDF, I want the pixels ZQ. So I have to do inverse of SK from here. to get the pixels corresponding to that PDF that I want. Okay. Now see the example. I think it will be more clear. Yes. No, this is one of the very easy examples. Not always is the case. Okay. And the important thing is how we shift it, how much. Okay. So you cannot have some formula. So you need some systematic way of doing it. So this is what we did. Okay. So you have this image. When I do the equalization, I get very bright. Okay. But I said, okay, not this one, but I want the CDF to be this way. Okay. And when I transform the image, it's still not very good, but still better than this one. Okay. And if I saw this, if you saw this, you can see this is flat, but still there are some here still. So even you can do some other engineering with it as well. Okay. Now the thing is, if I give you an image, how to do this in an image? Okay. So let's say you have 64 by 64 3-bit image, and we did this example before. Okay. So you have these are the values of the image from 0 to 7. Yes. This is the number of pixels inside that 64 by 64. How much time it's repeating? So it's repeating 790. This and this. Now what is the probability? 790 divided by 64 by 64. This divided by 64 by 64. You get the probabilities. Once you get the probabilities, okay, this is one of the table. Now this is specified. This is specified PDF. So what is specified PDF? The value of 0 should have a 0 probability. Okay, 1. The pixel 1 has 0 probability, 2 pixel, the intensity of the pixel should have 0, 3.15, and so on and so forth. Okay. Now this is what I want. This is what I have. Okay. So what was the step? First I have to equalize this. I have to equalize this. How to equalize this?
So this is actually the right one. It is a new pattern.
This is what's specified. This is what I specified. This is what I specified. This is what I have. Original image. So first I have to equalize them. So in order to equalize them, what I will do?
CDF.
CDF. So it's like easy. See, here it is just 0.19 multiplied by n minus 1, 7. Okay. 0.25 plus 0.19 and then multiply by 7 and so on and so forth. You get CDF of this and use that for transformation. Fine. So once I do that, I get this one. These numbers, which is rounded to the nearest integers. So this is equalization of image. This image. Okay.
Now here in ZQ, Z0 equals to 0, but how we found BZ of ZQ?
This is given. This is you specified. This is specified. Okay.
Yeah, this is good.
Given. Yes. Okay. So first, and we did this in slide number 27. Okay. Equalize this image. This is up to now we did not do anything. Now we have to equalize this one using the same pattern. Using CDF multiplied by n minus 1. You get these values. Okay. And we have to round it to the nearest integers. Now this is what we get after equalizing our own PDF. Specified one. Okay. Now what we did, we said, now this should be inverse of that to get Z0 and Z1. Okay. So let's see how to do inverse.
Derivation of the function.
How it inverse this function. Okay. No. So this is easy. Just a table mapping from there to there. So okay. So what we have here. Okay. Here we have the probabilities. Okay. So Z0 0 is this one. Okay. How from Z0 becomes 0, right? And Z1 was 1 becomes 0. Z2 is 0. Z2 was 2. Okay. So becomes 0. 3 was 3 becomes 1. 4 becomes 2. 5 becomes 5. 6 becomes 6 and 7 becomes 7. Okay. So this is my table right now. After equalize my own specified PDF. This is the second step. The third step is to find S is equal to Z inverse of Z. Okay, so how to do that? I have to see what are my S values. S values were 0 was 1, S1 was 3. So I have to use these values to find what it corresponds to Z. Okay, so let's say 1. 1 here is 3. So 1 becomes 3. Now I'm getting inverse. Okay, then we have 3. 3 becomes, there's no 3 here. So I have to find the closest one, which is 4. Okay, so 3 becomes 4. Similarly, 5, 6, and 7. So 5 becomes 6, 5 becomes 5, 6 becomes 6, and 7 becomes 7. 3 becomes 4 because we have to find the closest one. So 3 is close to 2, not 5.
Oh, there is 2 and 5.
Yeah, so I have to select 2 because 2 is closest to 3.
Okay, so there's no average.
No average.
Closest one.
The thing that's confusing me is, remember last class when I asked you how we can't make it completely flat because it's a trade-off between how much information we're using from the image. Where is this maintained? I feel like what we're doing is almost arbitrary. Like, where is this trade-off in all of this analysis?
Trade also, but we're still not making it very flat. But we are just trying to shift some of the pixel.
How do you know that we're not making
Okay, so flat. Okay, why we are not making too flat? Because if you have just flat PDF, what will the CDF look like? So we are not making this straight line.
Yeah, but by how much? We're just saying it's not flat, that's it. So anything that's not flat is acceptable.
No, it is again, it's based on your hit and trial or experience. There's no mathematical, no, there's no mathematical. But I know that I cannot make it flat. If I make it flat, I will lose information because I'm giving everything same probability. Okay, and if I just do like this, the other way around, still that is not the case. So I have some idea already that I cannot do it like this. I cannot go beyond this because if I do this again, I am going towards the other side. So I have to be somehow here in between this and the linear one. This I have the idea. I have the limits. Okay, in between. Now, how much in between? This I don't know. It is like hit and try. Okay, there's no some automatic way. But however, definitely that's some of the limitation of histogram matching, and this will lead us to the next topic as well. Okay.
Like when you use like data sets like deep learning or machine learning, that kind of stuff, that can
So
help.
this is what I'm saying. All these are methods. First, we saw the point processing. Then we say, okay, this has some limitation. Then we go to the histogram. Then now we go to the filtering, which is even better. Then we go to the transform domain, which is even better. Then we go to the deep learning. Okay, but every method has some limitation. For deep learning, we need ground truth. Yeah, not a lot of data, but we also need the ground truth. So where we get the ground truth?
Yeah.
The labeled data, the actual data. Okay. Okay. So these are some of the limitations. Okay. Okay. Then there's another limitation because sometimes now what we are doing histogram for the whole image. Okay. But sometimes this called a global method because we are taking the histogram of whole image, right? That's why it's called global histogram as well, whatever we have done. But this might not be good in some of the cases, okay? And I will show you which case. So what we can do, instead of taking the histogram of whole, I take the segments and take the histogram locally and do the equalization, do the equalization, okay? So I can give you an example. Let's say we have this image and you can see that there's some just boxes, black box and the white background or gray background, right? You cannot see anything. If I do histogram equalization, you will start for the whole image, you can start seeing something, right? Can you see that? There's something happening, right? Okay, but again, since I did this is the whole global equalization will not be good choice here because here there's some local information which is not global. Total information does not depend on this, and you can see that there's even the noise start to appear. Okay, and this type of noise is called yes, salt and pepper. Okay, because we see this is like salt and pepper, right? White and black. We'll discuss this. Okay. Now, but instead of that, if I just take 3x3 area and do the equalization on that 3x3 area, move again, do the equalization. So if you see, you can start looking into some points.
Okay. 3x3, that's some box in the figure.
Yes, it's like a sub image. That is just my image.
It's sort of like you mean that divide the image into 3x3.
Yes, and each 3x3 is itself, you can call it a sub image. That is, you are doing the whole process that we did on this 3x3. Then again, the other one 3x3.
So it's sort of like taking longer.
Yeah, of course.
So Victor, you are taking small areas,
Yes.
3x3,
And processing it separately. And this is the way, by the way, this is called segmentation. Even in deep learning, instead of taking the whole image, you take segments then, okay, and then process them, and this will speed up the process as well. Okay, and this is again, now see, I changed the size of the box, and you can see it's going better. Okay, so now the size, now the question is, what will be the size? No, it's again hit and try. Like the deep learning layers, 3x3 convolution is better or 7x7 is better, 5x5 is better. Okay, so one thing you have to make sure in image processing, most of the things are like hit and try or based on experience. Okay, like sometimes, let's say, if there are some minor details, maybe the 3x3 is better. Sometimes not here, like in deep learning, for example. Okay, but if you have like something, I would say very prominent, maybe 8x8 is better, not 8x8, 7x7. Okay.
So there's one question here: is the size, if the small size selection, give you better solution, or it depends on the
It
figure?
depends on the application.
In the application.
And the things you want.
Okay, so
so there is
it
no-
does not matter what's the size of the selection. No.
Okay. Okay, fine. So what are the limitations of histogram processing? As we have seen here, if I do, I get a noise. Okay. So one is the amplification of noise. I cannot add any missing information. Okay. If there's something is missing, a lot of details in bright and dark areas. If an image has a very dark or very bright pixels, histogram may map many of them to similar intensity, which we have seen in the example, which was very dark. Okay. So these are some of the limitations which will lead us to another thing which is called spatial filtering. Okay. So we have now the spatial filtering. Okay. What is filtering?
The same? I think.
What I did? I made this smoother.
Yeah.
How to make this smoother in time domain? Yeah, what I do, I just take some values here and average them, assign here. Then move it to another point, average them, assign here. So basically, averaging is actually a low pass filter.
Yeah.
Yes or no? Okay. And since we are in a spatial domain, we did not talk about the frequency domain. Okay, so here, what will happen? I will define a filter that will run over the signal, in this case, or image in our case, and will get you the value that you want. Let's say I want to smooth the image. So what I will do, I will define some small, this box, and try to, yes, average, and return the value, which you were discussing, right?
It's like the kernel model in CNN.
Kernel, we call it kernel, we call it filter or window, tablet, and kernel like
The same process.
the same process, right? Okay. So here, in general, this is what I told you before, that we define, okay, up till now we were just doing pixel by pixel, every pixel separately. Yes, in histogram it was a global. However, there was no neighborhood thing there as well. Okay, so here, what I will, if I have to find the value of this pixel, I have to take all the neighbors of that. Okay, and how I take, this is what I will, this is what the filtering is, that how to basically do this. Okay, so what point operations can't do? It is not combining the multiple pixels. Okay, it enhances the image, but it cannot extract the information or it cannot detect the patterns. Okay, so this is one of the limitations of this. I don't know if this pixel is going to give us something. No, multiple pixel means that you just, if you want to value of certain pixel, you also take the neighborhood pixel from multiple pixel.
Okay.
Combining multiple pixel has these applications. Either we can enhance the image, extract the information that we want, or detect the patterns. Okay. Okay, so again, this is some other the image filtering removes noise. It can sharpen the image, and you'll see how it's a very interesting method. Highlight contours, which is again sharpening, related sharpening, detect edges, which is again a part of it. Smooth images, which you all have seen here, the mean or something. Image filters can be a linear or non-linear. Linear filters are also called as the convolution filters. Non-linear operations are the either taking the mean or min and max. This you will see that what it means. Okay.
We said that the neighbors will make blurring, and then we say we'll make sharpening. So
Yeah, that's the beauty of it. Now, based on what I define in that box, will make either smooth or sharp.
because if we're just summing the
No,
it's
yeah,
summing divided by total.
yes. So this is what this is just smoothing, right? But what I did in the box, I said every number is just one. So all I multiply pixel and then add that, right? But what if all in that are not one? I will just show you the example. It's very interesting to see this. Okay, so here special fitting. If I apply averaging, the mean of that, I get very smooth image, and then I can apply the thresholding. Is one of the examples. Instead of applying the thresholding here, will give you a lot of dots. So if I am interested only the big ones, so I can do the smoothing and then the thresholding instead of doing directly thresholding. This is just one example I'm just showing you. Okay. Then again another example. If you want to remove the wrinkles, okay. So there is what the smooth filter can help. Okay. So like the filter in your mobile, sometimes making it smooth, removing the wrinkles. How it does just the mean filter. Okay, so let's say there's a special type of noise which is called salt and pepper. Okay, the properties we'll see later, but for now you can just see that it's like salt and white and black. Salt and pepper. Okay, so if you see here, you're seeing the black and white dots. Okay, how it will work? How to get white and black dots in an image? Yeah, so some of the pixel, what happens is some of the pixel goes to either high or low level. It becomes white and sometimes in the old cameras you notice that there's some red eye. Sometimes coming. So this was just pixel problem, the noise. Okay. If I apply mean filter to salt and pepper, it is still doing somehow good, but it's not better. Okay, so for this type of noise, the mean is not good, but if I take the min, max, or median, the other filters, it's doing the better job. Okay, so this is just I'm giving you an example. Still, we did not discuss the details that what is mean and what is max and what. Okay, fine. So sometimes one filter is better, the other is not better. And this is now the example of sharpening filter. If I make it sharp, you see this is much better.
What is
than
the original?
this is the original. This is the sharp.
How does it become sharp?
Now we use a sharpening filter. How these filter properties we'll see later. Okay, I'm just giving you some more. Okay, so that relation, if I want to convolve W with F, let's say F is the image or signal. Okay, W is the filter that I want. I want to convolve, so I will take F and W. I will flip and then slide it and find at each point. Yes or no? Okay. So how it is being done? A very basic example. I have F, I have W. Okay, so I have to flip it. Okay, and start multiplying, adding, and sliding. Okay, multiply, add, and slide. Multiply, add, and slide. This is what I'm doing. Okay, so how to do this? Okay, so first I have to flip it. 4, 3, 2, and 1. Okay, so this is the first, which is 4. Okay, then slide. So becomes 4 into 2, and this, and then add. Okay, become this. Then similarly 3 into 4 plus 2 into 3 plus 1 into 2 become this, and similarly and so on and so forth up till the end of the signal. This will okay. Okay, now for the image, definitely since we have now 2D, we have two variables. This is image, okay, and then this is a filter that you have to flip it, rotate it 180, because what we did there, rotate by 180 degree, right? So here also we have to rotate by 180 degree, and then the same thing, add, multiply, slide, add, multiply, slide, add, multiply, slide, and for whole image, okay, move one by one. First rows. Okay, so how to rotate an image? By 180 degree. Yes, so we have to flip horizontal and vertically to get 180 degree flipped image. Okay, or yeah, you can do like this. Okay, so this is flipping. Once you flip it, then you can convolve this to this, and this is filtering. This is filter, this is image.
Where does this come from?
No, this is just an example for that. This is an example of sharpening filter, but how it comes up till now, no. This is just I'm giving you an example. Okay, so how to do that? I will just place this filter starting. Okay, in the filter, in the image, where is 0, 0 location? Here, this is my origin, right? Because this was X and this is Y, right? But for filter, because this filter, my location is this one as the one, so this is my origin for the filter. Okay, why? Because this filter I have to keep it here, so my intention is in the middle. Then here, the middle one. Okay, you see what I'm saying? So don't confuse these two things.
Again, the thing that we're doing using the padding of 0.
Of course, we are assuming that everything outside is 0.
Yes.
Okay. Yes. Okay. So now I just place this one here. So 4 will come here. 4 multiplied by 2, then minus 1. Okay. But this will be 0 multiplied by 0. This will be minus 1 multiplied by what? Are you looking? Sorry. No? If you flip it, what it will be? If we flip it 180 degrees, what will be the result? No, we have to flip the filter, not the image. Okay, so filter, if you flip it, what you will get? So that's why so this is called a symmetric filter, which even flip will get the same results. Okay, minus 1 multiplied by 0, and then others here we have zeros, right? So we add it and assign that value to the middle, which is now this 2. Okay, then we move this one. Okay, again multiply, add, and then slide. multiply x, right? And then after that, another row, another row. So this is what the filtering is. Even the deep learning, they are doing the same thing. So what's the difference? What's the difference between deep learning and or the convolution layer on this one?
This is the defined one.
This is yes, this is the given one. We already, but if I have a convolution layer, I will try to find this that gives me this one. I have the output, and I will try to find this one. This is convolution layer, nothing else.
Values coming up. We need to adjust.
Yes, so you have to normalize and rounding should be done. Okay, is this clear? Okay, so I think this is what convolution is for us. Okay, and I think this is easy, right? Okay, now there's another thing that is very important, which is called impulse. Okay, what is impulse? Discrete. I'm talking about discrete. Huh? For that, you will define continuous one. Forget about the continuous because you have discrete. Yeah, but what is impulse? Discrete impulse function. This is just a one at zero location. One at impulse function with the height one is the impulse. Fine. So how we define it? Delta of x is 1 at x equal to 0, the origin, and otherwise it's 0. And if I want to define it in another location, which is x equal to x naught, I'll say delta of x minus x naught is 1 at this location. Okay, it has some properties. If I multiply this one with any function of any signal, what I will get? X0. Because let's say I have this signal. If I multiply with impulse, what I will get? Just this value multiplied with the value here, rest is 0. Okay, so what I will get? Function value at x of 0, yes or no? Yes. Okay, similarly, if I multiply this with another shifted version, I will get x at that location. Yes or no? Okay. If that is okay, then I think it's much better. Okay, this is the same convolution that we did. We have w, we have the f, and we just rotated it and found it out.